Peking University and the Simon Center.
Title is Transgression Forms in Khler Theory.
Thank you. So it's certainly a pleasure to speak here, and thank John for asking me to give this talk. So so this is probably a quite a general talk, at least for first half hour, and so for a few pages, and probably there's some people in the audience know much better than I do. But anyway, I want to talk about discuss these transgression forms from probably different point of view, and so just try to tell you there are something which we are doing now in Khler geometry are closely related to these transgression forms. So so first let me just say a few words about some generals, and so in a Hermitian geometry, so let's consider the vector bundle, holomorphic vector bundle, E over X. X is a Kähler manifold, and okay, thanks. Just start. So, so anyway, as I said, I will start with a few quite general things. And so E is a holomorphic vector bundle, and we know giving any Hermitian metric, we can compute the curvature of this metric. This is given by this formula. So in a local holomorphic frame, if and the metric is represented by Hermitian positive definite matrices, then we can write this in a more explicit form.
It's an inner product on the bundle. It's not a metric on the manifold, right? It's an inner product on the bundle. H.
H is inner product on the bundle. Yeah. So what's the problem?
No, just for keeping the audience from being confused. It's you say Hermitian metric, people might think it's a metric, Riemannian metric on the manifold.
I think that's what it is.
No, it's on the bundle.
They read the first sentence.
It's an inner product.
No, it's okay. It's on Hermitian metric on the E. So I said, now what Claude means here, I should put E.
The Kähler manifold has its own.
Yeah. Okay, so we will come to a Kähler metric in a moment. So, sorry. So the Chern-Weil theory says if I start with phi, which is invariant, and k-linear functions, and multilinear functions, then we can define a form, which is we just replace the variable by the curvature. So then we get the KK form, and the Chern-Weil theory says that this is a closed form, and it represents a cohomology class in this cohomology group. So of course, as it stands. So it's okay. Okay. So anything unclear, let you know. I write here. So of course, this form depends on a metric. So this is a metric on a vector bundle on E. Okay. So right now we talk about the metric on the vector bundle. So giving two metrics on the E, and so what is the difference? Since we say this Chern-Weil form depends on a metric, so first thing we know this is exact, and in fact it's also if in this time in this Kähler case is of this form, and of course in general it's exact. It can be leads to secondary classes, and so but in this particular case we are talking about. So this is can be written as a DD bar of things called the transgression form here, and it's so this form was implicitly given in this paper by Bott and Chern, but actually here I follow this paper by Simon Donaldson, and so he fleshed this out more explicitly in the early 80s. So, So to be more precise, we can express this form in as follows. So suppose I'm giving two matrices of R by R matrices, and we define this function on a matrices by in this way. Okay, so then now if we take a family of Hermitian matrix and on a E this time, so with I guess a loop, okay, with a loop of matrix. So then we can have this form, and it turns out this form is if it's a closed, if it's a closed loop, then this form is the image of D operator and D bar operator. So this is in the complex geometry. You can decompose this axial differential into a 1-0 part and the 0-1 part. Okay. So and H dot here means the derivative of this family of matrix. Okay. So of course I said that this is standard. So now following Donaldson's this paper in '83, let's define this form, transgression form, which as follows. Is just so this time this family of matrix is only a path. So an initial metric, it may not be same as ending metric. So this this way you can define this a map from this. I think this should be I'm sorry. So it depends on how you say polynomial. If a phi is a case linear function, so this time should k minus 1, k minus 1. Okay. So let me add. So since phi is degree of phi is k, then this should be I'm sorry for typo. Okay. Should be here. Okay. So this is 2k. It's a k minus 1, k minus 1 form, and by the previous fact I stated. So this as this modular these images, then this is well defined. Okay, it's independent of a path. So that's so it has some these basic properties. So first, it's an independent path in this space, in this quotient space, in the quotient space, because previously I said for loop, then this is in the image. Right. So this I get this is the point to check. So as in the what you did before. Yeah. so now we have this so this is dd bar of that gives you a difference of two Chern-Weil forms, and
so I mean you need the second line plus the one about the circle to get answer Jim's questions. Because you have to use one path and the other path, and the whole thing's a circle.
Yes.
But since it composes.
Yeah, but that's what I said. Yes.
Yeah, I mean you have to use the second line too, right?
You can do that too. So it's if a second line that's you say this h1 equal to h2, then this become boundary. Right. Yeah. Yes. But it's you can also say this is a corollary of that fact. Right? It's something. It's basically from this fact. It's from different paths. You get a loop. Okay.
Not exactly. But anyway.
Well, so that computation shows that it's well defined up to
this this quotient. Yeah.
Represented the path, you get the second statement.
Okay, anyway, it's
Or maybe the additivity is
it's just
obvious.
yeah.
That's just the fact the integral. Is it additive?
Yes, you can
That's
yeah.
Okay. I see. Yeah.
So of course this is also obvious just by definition, basically. Yeah. So basically here is everything is pretty obvious. I guess except the first one I need to check it. Okay. So then we have this functional who was first used by Simon Donaldson in proving a following theorem. So he tried to extend the theorem of this previous theorem on the Riemann surface. So he proved on the Kähler surface the existence of a Hermitian Einstein matrix on E if is equivalent to E being a stable. Actually, here probably show the Manford stable, no Chern. Okay, I mean it's going to be the. So it's a Manford stable. It's called a slope stable. But anyway, I don't want to go into that since this is just warm you up. Okay, so from this previous, this is the properties on this transcription form, and you can easily check this is well-defined functional. Of course, this functional is a function on H. Okay, but this functional, of course, depends on base metric. That's H0. But because this second property, you look at the property here, and you can easily check this functional has, even though it depends on the base metric here, but it's a critical point. Its critical metric does not depend on a choice of a base. Okay, so more or in other words, this the derivative of this functional is actually does not depend on base. Okay.
You have a function that's defined up to an overall constant. You just replace it with its extra derivative. It's multiply in one form.
Yeah, multiply one form. Yes. Yeah. So the theorem was generalized to high dimensions by Uhlenbeck and Yao for Kähler manifolds and Donaldson for algebraic case. Okay. So more generally, so this is just a simple, very simple extension of this, what I said on the previous page. So if you have a set of invariant functions, and if you have a set of vector bundles, and with could be with different rank, and then you can take a linear combination of these functionals, okay, and you get a new functional. Okay, so in a sense, this can be this functional. You can also let's still call this Donaldson functional is can be thought as the functional on a virtual bundle here. Okay, on a virtual bundle. So now, and to maybe I just say on this one in briefly. So what was the motivation of this Donaldson using this particular functional? It turns out, and it turns out this in his proof of the previous theorem. What I mean is this theorem here is this is very very fundamental theorem, and he used a key ingredient in the proof is to use the gradient flow of the previous functional. Okay, and when he used the previous functional, actually he used this particular functional. So it's so you take phi 1, phi 2, phi I, just the standard symmetric functions, and so the gradient flow he used is the gradient flow of this functional, and lambda is just some constant which can be determined. Lambda can be determined by a first Chern class of vector bundle and rank of vector bundle. Okay, so then if you do a direct computation, basically follows this basic 3 property I said before, and actually number 3 property I said before, you can find the gradient flow is actually given by this equation. This is a parabolic equation, and since it's a gradient flow and it's decreases this functional, and using that monotonicity, you can have some initial condition energy conditions, and which of course you need to do more to finish a proof. Okay. So now let me go to a Kähler geometry. So first let me just remind you. So this time the matrix, I mean the Kähler matrix. Okay. So a basic problem in the Kähler geometry concerns the Kähler matrix of constant scalar curvature, or in more general is concerned the so-called extremal Kähler matrix, which were something and first proposed by Calabi. So at least in today's in the Kähler geometry in the last few years, if you see about papers in Kähler geometry, probably most of the papers are about this extremal Kähler matrix. Okay. So that's why also I want to for rest of talk I will concentrate on this and show you some of this connection between what I said before and about this canonical matrix on the Kähler manifolds. Okay. So I guess this is just standard things. The Kähler matrix is locally written in this form, in terms of Kähler form, and then its nice property is a Ricci curvature is essentially given by volume form. Okay. So then the scalar curvature is simply a Laplacian of logarithm of a volume form. Okay. So now first, this is a variational problem to find the Kähler matrix of constant scalar curvature. How do we see that? So by the Hodge theory, the space of Kähler matrix with a fixed Kähler class, namely in giving a Kähler matrix, D is closed. It's a closed form. So this represents a Kähler class represents a cohomology class. Okay, and this is called the Kähler class. So if we are giving a two Kähler matrix, which is with the same Kähler class, then by Hodge theory, it says this only different by function. Okay. So in this way, you can identify a space of Kähler matrix as a space essentially as space of functions, of course modular constant functions, and also you need these positivity conditions. Okay. So you can here you can think this omega is a fixed Kähler matrix, is some reference Kähler matrix. Okay. So in the 80s, this Mabuchi introduced this K energy. So this is the original definition of K energy, and this is in quite a simple form. So this S here is a scalar curvature. So you can think if you just believe this function also is well defined, then if you look at if you compute a variation of this functional, the first variation of this functional, then you immediately see this scalar curvature has to be constant, and mu is a constant, and this constant again is determined by a topological constant things. Okay. So mu is a constant determined by a first Chern class of X and the Kähler class. Okay. So it's a topological number. So mu is given by this. It's nothing to do with a matrix. Okay.
Is there a dot over the phi?
There's a dot here. So phi is so omega t is a path from omega to this. So omega t should be written as a I guess here I use a phi for two things. So I guess this is and the one is with depends on t. One is without t. So I'm sorry for. So let me. So here is without t. So you can think here is a phi 1. Okay. So here is with a t. So of course you need to check one thing for this is because this to define this functional is I use a path. So then you worried whether it depends on a path or not. So in fact what Mabuchi checked is in this 85 maybe. So he checked that this is actually independent path. Okay.
So you're integrating one form that happens to be closed. So
What is one form?
if you think of the
Yes.
with respect to 0, 1 as outside.
Yeah. That's right. So, but so anyway, you're right. But this is let's see. Okay. So its critical points are Khler matrix, and this is very easy to see from this formulation. Okay. So and also I want to mention it's a Fataki invariant and Calabi-Fataki invariant. So this is defined as follows. So as it looks, it's quite somehow is disjoint from what I said before. So I take any metric, and since that's a scalar curvature, and this mu is actually, even I wrote over there, but it's actual average of scalar curvature, and then you can find you can solve Laplacian equation to get H omega. So of course H omega is not unique, but it's unique modular additional constant, and V is a holomorphic vector field. So this invariant was first introduced by Fataki for Fano manifolds. So then soon they both realized this actually can be done for these more general cases. So now what you need to prove here is this integral depends on omega, depends on metric, but actually you can prove this is actually what they proved is this is independent of choice of metric, independent of choice. So it becomes invariant on holomorphic vector fields. So and you can also check this actually is the character of the algebra of holomorphic vector fields. So then from this formulation has the different formulation have a different advantages. This formulation has immediate advantages. If you have a Khler metric of a constant scalar curvature, that means S omega is equal to this constant. That implies H omega is constant by maximum principle. So then the F has to be identical equal to 0. So F being 0 is an abstraction. So it is a holomorphic abstraction to an existence of Khler matrix with constant scalar curvature. Okay, the constant scalar.
So the thing that's not obvious is that this only depends on the class and not on the particular metric.
Say it again.
So the thing that is not obvious the first time you see it around seems to depend upon the particular metric that you're calculating on it, but actually it's only dependent on the
exactly. That's what I said. So it's what the point here is to prove these things here. Okay. So okay. But this formulation is easy to see these things here. Okay. So anyway, then there are a lot of Khler manifolds with non-vanishing Calabi-Fataki invariant. So those manifolds do not have a Khler matrix of a constant scalar curvature. Okay. So this is actually it's not the first abstraction, but it's a second. In my opinion, is a more important one. Okay. So then we mention a few simple facts. So if this first Chern class of a manifold is a multiple of a Khler class, then one can check by using a maximum principle a Khler metric of constant scalar curvature must be Kähler-Einstein. Okay, and it's then the uniqueness of Kähler-Einstein matrix was due to a Calabi long time ago, and in more difficult case by Bando-Mapuche in the 80s for positive case. So there are also this famous result of Yao for solving a Calabi conjecture, so which gives you a Khler matrix of with scalar curvature 0, and there's Aubin-Yao theorem, and in the positive case there are some this result. It's not completely solved in the positive case. So now let me come. So in the previous, I just want to tell you, remind you a few basic things about what we are doing in the Kähler geometry. So now let me see what is the connection between those canonical metrics and the transgression forms I mentioned at the beginning. So there was a simple observation that's actually motivated by this book of Fataki. So I will mention later. So it turns out this if you take this Donaldson type of functional, and you restrict that to a certain subspace or submanifolds in what I mean is a submanifold in the space of matrix, and you actually can get all these useful functionals in the Kähler geometry. Okay, and for example, the K energy I just mentioned, which is probably most used energy in today's study, so can be written as Donaldson type functional. Okay, restrict to a certain submanifold or space of a Hermitian matrix. This means on a certain vector bundles. Okay, on certain vector bundles. So let me just show you a few examples. Okay, so even though this writing this K energy in terms of these transgression forms is not probably does not help in certain technical issues, but it does lead to a class of new invariants and new functionals, and also using this fact you can study certain stability things. Okay, it actually leads to stability things, and so okay. So again, let's remind you this is 5K is the standard symmetric functions. So now let's L be a line bundle. So usually when I say a line bundle in this discussion here, basically means the first Chern class is given by Kähler class. So I want to look at the Kähler class, which is not only it's a real class. I want this to be an integer class. So that this actually can be expressed in terms of positive line bundle, in terms of the first Chern class of a positive line bundle. Okay, so the first example is you can take, for example, take this one. So in this Kähler geometry, it seems to be this. You always take function. It's probably not absolutely necessary, but we always take this symmetric function of degree n plus 1. It's dimension plus 1. Okay, so I compute this functional. By direct computation, you can check this is this. Okay, and maybe this is still too complicated. Let's see our next page. So if we look at on S2. On a sphere, one-dimensional case, complex one-dimensional case, then this function will just become this. Okay, so it's essentially just it's a functional we have seen for many times, for a long time at least. So for example, this functional is used is a functional for prescribing Gauss curvature problem, was studied by Nirenberg and those people for many years, and also. It's also in some like a paper of Osgood, Philippus, and Salak, because this is also determinant of Laplacian. Okay. So of course, how do you formally speaking, determinant of Laplacian just multiply all the eigenvalues, but you have to regularize that. Okay. And I should say, so this is simply is a special case of this functional. Again, this functional is also determinant of some operator. Okay, some operator. And moreover, you can compute the critical points of this functional, and so this time H0 is a Hermitian metric on the line bundle, and if you change a different Hermitian metric, it's only different by function phi. It's like you are changing the Khler matrix within a same Khler class. So then you can compute the Lagrangian equation. The first variation of this functional is just this Monod-Ampere equation, so which is used to solving this to prove a Calabi-Yau theorem and Aubin-Yau theorem and so on. Okay, so this is one thing, and you can also interpret Mabuchi energy. Mabuchi energy is also a constrained version of a Donaldson type functional. So this is gets a little bit more complicated. So that's anyway, I fresh out. So this time you consider this set, this HL plus. L is the same as before. Is the polarization of this Khler matrix. Is given by Khler class of a matrix. So it's a set of Hermitian matrix with the curvature positive. Okay, and so that gives you a Khler matrix. This gives you a Khler matrix, and so then you can set one can induce a set of matrix on these line bundles, tensor product line bundles. So this is just the anti-canonical line bundle. So in this way you can embed this H with this property into a space of this like a product, the space of Hermitian how do I say? So it's like a space of Hermitian matrix on this set on the union of vector bundles or on a certain virtual bundles. Okay, so its virtual bundle is made of these things here, and then you can check these K energies of also this form. So in short, the K energy is also the constraint version, is constrained to this submanifold. It's constrained version of Donaldson functional, and okay. So because of this, in fact, in the early 90s, I wrote a paper. It can be also written as all this K energy can be written as in terms of eigenvalues of in terms of Quantum matrix, for example. I don't want to go into that. Okay, so the third example I don't want to give you, so I just mention it. One can also define a family of functionals on the space of Khler matrix in this way. For instance, in the later 90s, Xiu and I introduced a functional set of functionals, actually n plus 1 of them, and F0 is just a K energy, is just K energy, and F1 is something new. And using this function, we proved the space of Khler matrix with a positive bisectional curvature is path connected. Okay, so what we actually did is the space is clear. You just take by this solution of Frankel conjecture for space for any manifold supports this kind of matrix. It must be a holomorphic CPN, but just consider the matrix on here, and suppose the bisectional curvature is positive. So okay, so then what we did is we basically say we evolve this metric by Kähler-Ricci flow, and converge it to a standard metric in the limit. Okay, so F1 plays a very important role in this proof. So also the transgression form gives rise to a holomorphic invariance, new holomorphic invariance, and so as I mentioned at the beginning, this is actually I was inspired by this book by Fataki. So and it seems to be some people here must see that it's somehow I thought even that time I observed this, but it seems to be some general fact. Okay, so for example, you take a holomorphic vector field, and you take E can be virtual. So then you look at this integral. That's basically transgression. What's defined the transgression form. So only thing you require the degree is n plus 1, then you can check this is always independent of choice of metric here. It's an invariant. It's an invariant. Okay. So this is the exact the derivative of this. Okay. And so this is a different way to, for example, in particular, as I said before, it's maybe on the next page. So for example, you apply this to K energy, then you get this Calabi-Fataki invariant is equal to a derivative of K energy along the one primary family of automorphisms. Okay, so you can prove this. So then it is also one of above invariants from a Bott-Chern class, namely defined in this way, can be written in this form. Okay, so writing this way, then one can compute this previous invariant at the first for first definition I show you is given by integral for along certain metrics. Okay, so now it actually can be computed by this transcription by localization formula. For simplicity, I only assumed this is V has isolated zeros, but this is not. You can have just like a Bott residue formula, except the denominator is numerator is different. The denominator is same as in a Bott residue formula, if V has non-isolated zeros. Okay, so reading this way, you can actually compute the Calabi-Fataki invariant by just looking at the zeros of vector fields. Okay, and so on the other hand, if you have a good matrix, canonical matrix, like Khler matrix with constant scalar curvature, then giving that Khler class, then you have a vanishing of invariant. So the zero of this vector field has to be somehow balanced in the balanced position. Okay. So, and somehow I think this should be known fact. Okay. And I said the Fataki proved this in the case when the first Chern class is equal to omega. So what Fataki did is this case, and he used the Calabi theorem to prove that. Then I just realized if you write things in terms of these Bott-Chern classes, you don't need that. It's automatic. Okay. So now I want to discuss more things to go here from Fataki invariant to more things. So again, this is a rather general factor, which I just stated now. So it was shown by Mabuchi and Sams, and later reproved by Simon Donaldson, that the K energy is actually convex on the Hessing on the space of Khler matrix, with a fixed Khler class, and with respect L2 matrix. Okay, so more precisely, this means the following. So I said before, this is a space of Khler matrix with a fixed Khler class. It's just all the function phi, such that this omega plus the square dd bar of phi is positive, and quotient by equivalency relation. So namely, phi is equivalent to phi plus constant. Okay, so the tangent space of phi can be identified with psi, and suppose this is omega phi, and this is just the average of so the L2 metric on this, you just take a psi 1, psi 2, defined to be a psi 1, psi 2, omega phi n. Okay, so this gives you an inner product. Okay, and by computing a Hessing of Donaldson functionals, or computing one more derivative of Bott-Chern classes. You can check in case of in some cases you can prove the function is actually convex. Namely, you can prove Hessian has certain positivities along the geodesics. Okay. So in view of classical facts on the convex functions, so we expect its critical points. So in this case, if we apply to K energy, then this critical points are simply Khler matrix of constant scalar curvature. So we expect they are unique, right? Because convex function, if it has critical point, it should be unique. So just think it's the most classical case. And also, if it admits a Khler matrix of constant scalar curvature, only if a K energy is bounded from below. Okay. So it's also a simple fact about convex functions. So these were confirmed by Xiu Chen and myself, and the case for algebraic manifolds was proved independently by Simon Donaldson by different method. So the criterion, we can also use this to interpret a criterion for existence of Khler matrix for constant scalar curvature should be equivalent to properties of K energy. So this is what you can also see, make an analogy with a classical case. So classical case, if I have a convex function, okay, so if it could have like unbounded, right? And if it's bounded, then it's somehow either you have a critical point. So that's three cases like this. Okay. If there's a critical point, then this function has a proper. That means once you go to infinity from either side, this function should go to infinity. Okay. When the t goes to infinity on either side, this function should go to infinity. Of course, so this corresponds to a stable case. Okay. In the GIT, corresponds to things in geometric measures, invariant theory, this is just a stable case. And this is a semi-stable case. Because it could be still bounded from below, but it has no critical point at finite time, at finite point, and it's unbounded. So this is unstable case. Unstable case. So this is a well-known fact. So what we have been trying to do is simply try to do the same for these infinite dimensional spaces. Okay, for this K energy as a function on the space of Khler matrix. Okay, so again, this is a case correspond to this. We need to check this. So the properties leads to a notion of K stability. So, but the properties is it thinks this is infinite dimensional problem. So this is like a function on the space of functions. So and to prove a properties like you want to prove some nonlinear inequalities, is seems to be a it's good to have it, but still we hope to have eventually have an algebraic condition. So that's why we want to explore further to see some to see what the problem means in the algebraic sense. So to see that, let's just give you and remind you one theorem I proved in my thesis. So turns out we have this Kodaira embedding theorem, which says if you have a positive line bundle, if you raise this line bundle many times, tens of many times, you will be able to get the embedding by using a basis of this. But of course, the choice of basis is not unique. So then we get actually a set of Khler matrices. You get set of embeddings. For each embedding, you pull back the standard metric on the projector space, and then normalize it so that this Khler class, cohomology class, stays the same. Okay, so then you get a set of Khler matrix, and such a set can be identified with this metric space. Okay, so why is that? Because if two invariants are different by orthonormal transformations, then the corresponding metric will not be changed. Okay. So in my thesis, I proved this. So the space of Khler matrix with a fixed Khler class, that is this. I do this normalization here, is actually the closure of this in the C2 topology. So later on, by Weidong-Rang and Zerdish or Katlin independently, they proved actually this closure is also true in the C infinity topology. Okay. So what is K stability? The K stability, in short, is simply the polarized this Khler manifold with this fixed Khler class. Is K stable simply means the K energy respect to each of these is proper. Okay, I guess I didn't miss something. So it should be here is the K energy respect to each of these is proper for L infinity large. Okay, I'm sorry, I dropped something. Okay. So I I repeat it. So somehow we from the classical fact we expect the existence of this good matrix is same as the properties of K energy. So now we want to interpret these properties in terms of algebraic terms. So one way to do that, you just simply restrict your K energy to a finite dimensional case. So for this set of a finite dimensional space, and what is then try to interpret as this stability condition. Okay, so before I do more algebraically, this is the faster way of defining this. Okay, and there is this Faulkner conjecture about this, and we probably already mentioned a few times. So now we fix the embedding, try to interpret these properties. So this time we are talking about this K energy omega restrict to this finite dimensional space. This is basically isometric to SL n plus 1 quotient by SU n plus 1. Okay, and this is I want to say in terms of more algebraically. Okay, so there's first way. Originally, when I did this, I just did in the most naive way, and as I said on the previous transparency. So I check for any one parameter family of this in view of this Hilbert criterion. We check in order to check stability. You check stability on every C star subgroup. Okay, this algebraic one-dimensional algebraic subgroup. Okay, so then you because it's algebraic, everything is complex. There's a limit, and then assume this sigma x non-trivially on the x0. Actually, assume sigma has to x non-trivially is somehow was actually when I would define this, I put more condition x0. But later on, there was a period and the people somehow try to do it more generally. But it turns out that actually one needs to make some actual assumptions. This is actually a contribution of the Chi and Chen-Yang Xu. So anyway, and these assumptions, you can compute this the derivative of K energy and take a limit, and you can prove this limit exists. Okay, so that's actually I did in 1992, and in that time when I did it, I should say is I assumed x0 is as simpler singularities. Okay. So then the definition is XL is K stable with respect to this particular embedding if this weight, this limit is negative for every sigma, for every C star group, subgroup. Okay. So there was a more algebraic version of this K stability. This is let sigma x0 as before, and let L0 to be a restriction of this line bundle, and ambient line bundle restrict to this x0. You know x original in some CPN, and the sigma x on this. So you take a limit, and the limit goes to x0, which is certainly still as a cycle here. It's still here. So here, okay. And then so you have some standard plane line bundle here. This is a hyperplane bundle here. So you restrict to these things. That's L0. Okay. So now this time, the action sigma action acts on these cohomology groups. Okay. And then there are two later things. One is the dimension of this cohomology group, and second thing is the weight of this action. So this is simply you look at determinant of this, and then become a complex line. So you act on this, you just be given by some weight. So it's a standard fact in algebraic geometry. Is this is a polynomial? Both are polynomials. This simply by this Riemann-Roch theorem. Say this is polynomial of this type, and this it turns out the weight can be also written as some polynomials, and this is polynomial degree n+1. Okay. So then Donaldson defined his version of a Fataki invariant as in terms of coefficient with that two expansions. So it follows from localization. This one is equals to a previous one if x0 is smooth. Actually, in normal case, you can also do that. Okay. So then Donaldson defined the K stability in this way, if for every. So this should be FD. Okay, FD here. So this is and so before I go on, I should remind you why we do this. So we fix the x and line bundle. Okay, I want to say existence of a Khler matrix with a Khler class. Say Khler matrix omega with Khler class equal to first Chern class is line bundle, and the scalar curvature is constant. If and only if I want to say, no, that's a conjecture at least, right? Conjecture this equivalent to this XL is K stable. Okay, so in between this, what we did is first we say this should be equivalent to this K energy is proper. It's proper. Okay. So then what we consider what is here is in this diagram. This is say this one for each fixed L for fixed this inbanding. This K stable is simply means M omega restrict to this 5-dimensional case is proper. It's proper. So what I'm doing now is simply tells you what this means in terms of a different algebraic language. Okay, in terms of Fataki invariants, in terms of this Donaldson type of Fataki invariants. Okay, and of course, how do you go? So I already say this is proved. So how do you go from this? You need to go from 5-dimensional case to an infinite-dimensional case. So that's usually the analytic step. You need to do some a priori estimates to reduce the infinite-dimensional problem to 5-dimensional problem. So, which I'm not going to talk about here. Okay. So, so now, in the last few minutes, I want to say give you a more recent version of K stability. So all this I just show you there's some interesting geometry behind this. Okay, I mean what we started is simply say some function is convex, is proper, and one try to interpret this. Okay, so this one seems to be, in some sense, is more interesting. It's because time I cannot give you a full version of this. I just try to do in a fast, quick way. Okay, so this Chern-Weil introduced this new version of Khler stability, which actually contains more information. So he defines this in terms of hyperdiscriminants. Okay. So what is hyperdiscriminants? Of course, it's this generalization of discriminants, which he probably can expand better. So again, we assume X is embedded in some projective space. So then you can generate more embeddings. Okay. So one particular embedding are given by so-called Segre embeddings. So for each R, you multiply this by X by a CPR. So then this will be in a. So maybe I make it more precise. So you have X original in the CPN. Then you multiply this by a CPR, sorry. And then this will be contained in a CPN cross with a CPR. That's clear because this contained there. Then second embedding is this to embed this into a bigger project space. Okay, by some polynomial functions by two variables. Anyway, so you can compute that's actually not important. You can compute the dimension of the Segre embedding. Okay, so you can do this for every R. For every R. So here I only pick up 2 R for which concern us. So then for each of these R, what you have is you look at all hyperplanes which contain at least one tangent space of this embedding, and you can check it from a hypersurface in the dual project space. Now, what is dual projects? Dual project just given by a set of all hyperplanes. Okay, and this is a classical fact. It's probably back to Kenny or many people. Okay, so you can check. It's also direct. It's more classical algebraic geometry. So you have a hypersurface, and the R's this hyperdiscriminant. I denote this. Is simply a defining polynomial with this hypersurface. So I give you a hypersurface in some projective space, which is always defined by some homogeneous polynomials of. So if I have a hypersurface in some CP_NR, so this is always defined as the zeros of a polynomial in a homogeneous polynomial in a homogeneous. Okay. So it's not unique, but it's unique up to a multiplication by constant. So it's which will not affect all the discussion in the following. Okay. So I call this this is called hyperdiscriminant. Okay. So I just remind you this if you take R to be n, this actually coincides with the Chern form, which is you can define in the Kähler Chern form is in a different way. Okay. So now what we did is so the stability, Khler stability of Chern-Weil is actually gives a non-trivial relation between these two polynomials. More precisely, how we do that? We take any maximized algebraic torus in this linear group. Okay, so then we consider this character lattice. Okay, and it's well known. This is isomorphic to z to n. Okay, so I guess n here must be should be nr now. Okay, it's the corresponding space. Okay. I'm sorry, n is just n. Forget about that remark. So then you can set these to be weighted polytop of these polynomials. Through the reduced representation of G in the space of homogeneous polynomials. So what I mean here, since this linear group G, okay, and because of construction here, we'll induce action here, and we'll induce action here. Eventually, we'll induce action here. Okay, so now I have some polynomials here, and since I induce action here, and H also induce action here, and it's a classical factor H. You can choose a monomials here, so that all the monomials are eigenfunction of these actions here. Right? Then each eigenvalue give you a character. So how do you define giving a polynomial define a weighted polytop? You just you expand this polynomial in terms of monomials. For any non-zero coefficient, you find the character, and that character will give you a point here. Then you take a convex hull of that. You will get this polytop. Okay. So and you do this for each R. And what Chern did is say for simplicity I use a semi-stable here, because stable you need a bit more condition in order not to make a mistake to talk about these polytops. Okay. So I just try to save time. So he also defined a stability. So I say K semi-stability here, if and only for any maximum torus H, we have these we have two polytops, and one has to be contained in another. And stability means this one has to be strictly contained in another, but it's how this strict means you need to specify, because I don't have time. I don't actually. Frankly speaking, I'm not sure I'm the best person to specify this. Okay, so this is a nice interpretation of stability, and originally I tried to draw the picture, but I found it's a difficulty for me to do it on this transparency. So instead, I show you one particular consequence of that, which at least tell you classically this means something. Okay, so for example, this has some many geometric consequences. Let's just pick up the simplest one. You take a plane curve in the CP2. That's a very classical subject. Then look at the dual curve. So this time you don't need to take R, because N is 1. R is nothing to do. Okay, so you just take all the lines. So what is dual? It's all the tangent lines of this. Okay, so you take give you a dual curve. So I guess sorry, this is not the page. So, but I want to. So this is just all the tangents of this contain the CP2 dual. Okay, and it turns out these things particularly imply this is stable, namely, and semi-stable means its weights. If there's some C star action acting on this, SL to L 2C action on this, the weights has certain properties. Okay. And this is true for any dual curve. So this actually, I don't know whether there's other direct proof of this, and I don't think there's a simpler proof, because at least it does not have a simpler proof, because indeed, in general, this dual curve always has singularities, because you might have a tangents, which also tangent at another point or another 2 points.
Yeah,
Give you
double points.
double point give you
At least 3, right? Then it's
yeah. So you might have 3 tangents. 3 tangents give you a cusp, or 4 tangents. So and also it's a known fact. For example, you go to a Manford's block, GIT block. It's many singular curves are not semi-stable. So, but dual curves are always semi-stable. So that means something on the configuration of singularities. So I stop here. Thank you. Okay, so sorry for overtime. Yes?
You referred to this curve being stable, but the symmetry of the group is CP2, right?
A symmetry group of CP2. That's so
Curve is stable. I thought that was related to the orbit structure. It's not an orbit.
it's not orbit. It's an orbit in this. So let me put it this way. So defines this is in the CP2, right?
Yeah.
So X. So and you have a group is SL to R to C. Okay. So but this is induced action. So this is defined by polynomial of degree D. D dual, okay. So then this induced action on the space of polynomials.
Yeah.
So then you look at that orbit is closed.
But how's it related to the curve?
Curve is here. So X is so then you look at dual curve. So this is dual curve.
Yeah.
Okay.
I don't see how the action has anything to do with the curve. You're giving a property of the curve in terms of the action. So what is the property?
The action is on here,
The dual space.
on the dual space.
Yeah.
Yeah. And the action is on the dual space, and and since this curve is defined by polynomials, so you
Take that
action
point.
on
Okay. And then
it's a point in the space of so F is a space of PC projectified of polynomial of degree D. So that's you mean.
and then you can look at the orbit of that
Yes,
polynomial.
exactly. That orbit needs to be closed.
Okay. Thank you.